Okay, everybody, moving on to unit number 9 in this year. And we're going to talk about gas laws, liquids and solids. We're going to start with gas laws and then move on through liquids and then talk about a little bit about solids. But most of this unit is going to be basically on looking at gases. All right, so just to begin, a couple of things on gases that we want to keep in mind along the way. All right, and that's some physical properties of gases. Now, again, gases are unique in the way that the particles are moving around a lot and there's a lot of space between them. So because of that, they have certain properties that the other two phases don't, liquids and solids. Okay, so moving on a little bit. Okay, basically gases are compressible and they also expandable, right? So we can compress a gas into a smaller space fairly easily, and we can also expand it out. Okay, gases is the phase that can fill a container completely. All right, it doesn't have a set volume. Okay, now again, they're going to assume the shape and volume of any container, and the fact that they assume the volume of the container, okay, is an interesting part of gases. All right. Next, mixtures of gases are going to be infinitely soluble in one another. Okay. So again, mixtures of gases will always mix because of the space between them. Okay. Gases are going to be affected by temperature and pressure. All right, and that's kind of unique as far as liquids and solids go, because again, pressure is going to be the new kind of a new thing we really have to study a little bit here, because that concept of pressure is going to be very, very, very controlling to gases. So basically, you can see high pressure. If I press this plate down here, I'll take these gas particles and I can kind of smash them together here and reduce the space between them. And if I lower the pressure by pulling this plate back, you can see how I allow these particles to kind of move around and spread out a little bit. So high pressure would be pushing this down, low pressure would be pulling the part here, and you can see what happens to the volume as a result, right? You have a lower volume here, so you can think about a low volume here, but you have a very high volume here, looking at the space the gas takes up. Okay. Again, gases are also less dense than solids or liquids. Okay. As far as gas pressure goes, okay, gas pressure is simply um, the force of collisions of gas molecules against the walls of the container. Okay, and that determines what gas pressure is. So if you look at the diagram to the right, you'll see these particles are kind of bouncing off the walls of this container. And again, the more particles you have, the more gas you have within that, and the faster that they're moving, the more pressure, the more impact they'll make on the walls of the container. And that's simply what gas pressure is. Now, the top of the atmosphere here, okay, is really a certain. So if this is you down here in the bottom and this is the surface of the Earth, the weight of the air in this column is actually forcing downward on top of you. So if you were standing here on the Earth, okay, and you were here, you would have this column of air down here. Usually we call that 1 atm, and that's the impact or the air as it pushes on you in all directions in this unit of area. So we're thinking about a force that you're placing down over some type of area which has a square footage to it, right? The square spot. So force over area is really how you determine pressure. It's the amount of force over the area. Okay, and usually what we do in the English units, and again, is pounds per square inch, right? How many pounds would you put per square inch? Okay, the atmosphere would put 14.7 pounds on every square inch of surface. Okay, that's what air pressure would be like. Now, again, this is in pounds per square inch. In science, we use the metric system, so we'll have more about that later. But I just want to show you what pressure is defined as. Okay, and again, the more the force that you put on a lower area, the stronger that pressure would be. Okay, so just to give you an idea about the gas particles. All right, as far as measuring pressure, I'm going to go through this really quickly. Torricelli was an Italian scientist who did some work with this. Okay, and he built this barometer. A barometer measures pressure, and what he did with this barometer was he put this dish of mercury in a dish, and he filled this mercury tube up to the top with mercury. Okay, so he filled the dish completely and the tube completely, and then inverted the tube upside down in the dish and realized that this column of mercury would actually be supported in here. Okay, and it did drop from the height down to some level. Okay, and that was important to know about his barometer. Okay, so basically, he realized that atmospheric pressure pushing down on this dish in this direction would cause the height of the column to be pushed up to this height. And really, air was really responsible for keeping this pressure or keeping this height at this level. Now, in the top of the tube, there is no air here competing with the pressure pushing down. So the only thing that is measured here is the pressure pushing up. So the height of this mercurial column is the absolute determination of the atmospheric pressure. Okay, and the height of this column was 760 millimeters of mercury. So that becomes a measurement of air pressure. So mercury in the tube is pushed up by the force of atmospheric pressure. Okay, the height of the mercury column changes with changing atmospheric pressure. Again, so if you were to take pressure off this, if this atmospheric pressure should get weaker and would push less, that would allow this tube of mercury to go down a little bit. It would drain into the dish, right? Because less pressure was pushing up. This would push down, or this would come down, and the height of mercury column would be less. If you increase the pressure, then the height of mercury column would rise. Okay, so at normal atmospheric pressures at sea level, okay, what we do is we measure 1 atm. So at sea level, if you were standing at the beach at sea level, typically you would have 760 millimeters of mercury. Now, one easy way to do that is to change the unit to something a little bit easier to read. So we call that 1 atm. Okay, is the same thing as 760 millimeters of mercury, and the same thing as 760 torr. Now, torr is just the first part of Torricelli's name. Okay, so they attribute this to him as a unit. So 760 can be either millimeters of mercury or it can be torr. All right, and the metric unit for this is a pascal. A pascal is also a unit of pressure. However, this is a very small unit of pressure. So we have a kilopascal. Okay, and this is also 1 atm. So 1 atm and kilopascals is usually what you see, but you could see torr and millimeters of mercury as well. So there are 4 different units measuring the same atmospheric pressure at sea level. Okay, table A in your reference table will also give you standard pressure. So this is standard pressure. Okay, normal atmospheric pressure is standard pressure. All right, so make sure you know what standard pressure is. Okay, again, as you move down in the atmosphere towards the surface of the Earth, pressure, the weight of the atmosphere is greater, so you have greater pressure down here at sea level. So if you were standing here, you would experience this column of air pushing down, and that's what surface air pressure is. All right, so that's important to know about air pressure. Okay, so if we would convert 350 millimeters to ATM. Again, you want to be able to go in between these. You could set up a simple calculation. You could say 350 millimeters of mercury, okay, is to 760 millimeters of mercury, okay, as X ATM is to 1 ATM, okay. So here is your conversion between these two, okay, and you can set up your thing, or you simply can do your 350 millimeters of mercury, and you can say 760 millimeters of mercury in 1 ATM and do it by dimensional analysis. So either way, you could figure this question out. I'll let you calculate it and get the answer. You can see it's probably going to be less than an ATM because 760 is equal to 1. So 350 must have to equal to less. So I'm going to count on you to be able to convert these. Okay, should be pretty easy. All right, so that's Torricelli's barometer. Again, if you lower your atmospheric pressure, and again, he did this by going up on a mountain. Like if you go up on a mountain, again, if I drew a little mountain here, if you go up on a mountain, you have less air pressure, less atmospheric pressure would have this lower, okay, and you would be able to read the atmospheric pressure. Okay. All right, so we go into defining what a gas really is, and we use the concept of ideal gases. Okay, this is a little bit out there. It's a little bit conceptual, and you really got to think a little bit. But I'm going to try to use a little bit of analogy. We all have our favorite food, right? And to be really quick, how do you know that food is really great? Well, you have an idea of the perfect food. So, for example, if you're watching a commercial on burgers, or you watch a pizza commercial, or you watch anytime they're cooking food and it really looks amazing on TV, that's because they try to show it to you in perfection. Now, why do they do this? Because they want to make you buy that food. And then what do? You go to a restaurant, or you go to the pizza place, or you go to the burger place, and you usually get the burger or the pizza or the food that you like, but it's never exactly how they show it, because how they show it is perfection. All right. So what we want to do is we want to define a gas where a gas would work perfectly when we calculate. So how do we create the perfect gas? Okay, so to give you an idea how we actually do this, um, based on experiments, scientists actually find that okay, that all gases behave similarly. So based on their calculations, they find out that all gases, now this is all gases, no matter what the gas is, behave similarly and follow basic mathematical laws with regard to moles, pressure, temperature, and volume. Okay, so what they find is like when we manipulate these, most gases will behave accordingly, okay, to these changes in moles, pressure, temperature, and pressure and volume. So we're going to define the perfect gas that would behave perfectly when it follows the math. So, what's the perfect gas? Well, how would a gas behave perfectly and follow exactly the math to the T? And that's what an ideal gas is. So, let's define this perfect gas, just like you would define the perfect piece of pizza. Like, if you had a perfect piece of pizza, how would you define that perfect piece of pizza? Okay. So, basically, gas molecules are going to be in random straight line motion and have no attraction for each other. Now, the fact that they have no attraction for each other is a little bit weird, right? It's not exactly true, because we know that all gases and all particles have some sort of attraction, whether it's London forces or dipole forces or hydrogen bonding. We know there is some. Now, because gas particles are far apart, we're going to assume that they have no attraction for each other. Okay, but that's going to be an assumption. So in this picture, you can see that this particle here would not have an attraction to this particle here. However, when they pass each other, they may. But notice that the space around them is so large that we're going to assume that there's so much space that there's no attraction. Okay, number two, the volume of each gas molecule itself. Again, the individual molecules themselves, we're going to assume that volume is zero when compared to the size of the whole container. All right, so what does that really mean? We're gonna mean here that each pinpoint molecule here, we're gonna assume has no volume. Okay. Okay. Now again, can we assume that all the time? Of course not, right? Particles do have volume. They are made of mass. So points 1 and 2 here, it's a little bit of a stretch. We're assuming that gas particles have a volume of zero, okay, and have no attraction. But we're just assuming that. Just like with the perfect piece of pizza, we're assuming that the crust was baked perfectly. We're assuming that the cheese is perfectly cooked. We're assuming that the tomatoes are perfectly fresh. Am I making you hungry? And that whatever you put on the pizza, whether it's pepperoni or whether it's mushrooms or whether it's whatever you want to put on it, vegetables, that they're all cooked perfectly and everything's great. So we're assuming this, even though we know most of the time it's probably not true, right? All right. So, and again, compared to the size of the container. So we're going to assume that the container that you put the gas in is so huge that the particles compared to the container are super tiny. Okay. Next, gas molecules are going to collide with each other and with the walls of the container to produce something called gas pressure, but there is not going to be any change in total energy. And that simply means these particles are going to be bouncing around randomly, random straight line motion. They're going to hit each other, bounce off. They're going to collide with the walls, okay, and produce pressure when they hit, okay, but they're not going to be settling down and and changing their speed to zero. They may affect their speeds, but the average energy stays the same. Okay, the average kinetic energy, which is again motion, don't forget that the motion of the gas particles, okay, is proportional to the absolute temperature, okay, and that's going to be in Kelvin. Kelvin, really important that you're going to be in Kelvin here. All right, so that's going to be very important. All right, so a couple of things to realize in ideal gas. Now, ideal means never going to happen, right? This is an ideal situation where if you did a calculation with moles, temperature, pressure, and volume, this perfect gas would follow all the rules of gases perfectly, just like the perfect piece of pizza would be the perfect piece of pizza. Everything fresh, everything freshly cooked, perfect taste, everything. We know it doesn't exist. It only exists in commercials. So now we have something to compare things to this to. What I would make sure, and again, page number 3 and number 4 are kind of self-explanatory here, something we've kind of looked at before. It's the no attraction and zero volume where you're going to have to really watch. Okay, so that's really important. Okay, so next, what do we deal with when we deal with real gases? Now, real gases, which are gases that exist in real life, this is the actual piece of pizza that you get. Okay, they do have attraction to each other of differing sizes, right? We can have dipole forces of attraction. We can have London forces. And again, the dipoles depend on the En difference. Okay, right? The electronegativity difference between them determines the poles or the dipole forces. Again, London forces, how big is the gas? We don't know. So they're going to have attraction. Real gas molecules are going to have individual volumes based on their size, right? Okay, so that's going to happen with a real gas. Okay, real gases, okay, are going to approach the most ideal conditions on the conditions of high temperature and low pressure. Now let's just think about this for a minute. Okay, if you have attraction, now again, if you think about this here, if you have attractive forces, so if you look at this here, this is going to become your ideal gas in this picture. Okay, this would be your real gas. If you look at your real gas side, your real gases, again, are going to have attractions between those particles. Those blue lines represent attractions. Okay, now again, how would you take those attractions and make them similar to an ideal gas where you would have no attraction? The only way to do that is to take these molecules and drive them apart further, right? So we want to take a real gas, and in order to make it mostly like an ideal gas, we would want to bring them apart, pull them apart. And how would you pull those gas molecules apart more is by raising their temperature and lowering their pressure, right? Taking the temperature and heating them up would cause them to be driven apart. And lowering the pressure by increasing the space here would allow those particles to separate. And then they would be like this in this real gas where they'd be separated. Okay? So your high temperature and low pressure would be the best, most ideal conditions to doing this. Okay, so most ideal conditions, of course, also are the lightest gases. Again, lightest gases will have less forces of attraction. Okay, so hydrogen and helium, since they're the lightest gases, are the most ideal gases in the periodic table. They're the ones that approach perfect gases because, again, they're the smallest. They would have the smallest individual volumes, and they would have the least attraction because they have the least a number of protons and electrons, right? So those are the lightest gases that would be most ideal, okay? So real gas, ideal gas. Again, with the pizza, the most ideal pizza would be the best restaurant, right? If you went to the top Italian restaurant in New York City or the top Italian restaurant anywhere, you would probably get the best tasting pizza, right? If you went to a low-level Italian restaurant or Italian restaurant that's kind of cheap, you'd probably get a piece of pizza that was just average, all right? So again, the best tasting or the most ideal would be the lightest because those on average are the furthest apart and have the smallest particles. Okay, so under which conditions, so if you think about this, and I'll give you a simple way to remember it, under which conditions would a gas be most ideal? Again, you're thinking highest temperature, lowest pressure. So let's take a look. If we look at A and C, A and D, they have the highest temperatures, right? So you're looking for a high T and a low P. Okay, so the highest temperature would be 300. The lowest pressure would be your 0.5. So high temperature and low pressure would be choice D. Okay, and a great way to remember this is the acronym PLIGHT. Okay, so this means pressure low, okay, ideal gas, high temperature. Okay, so there's your PLIGHT. Pressure low, ideal gas, high temperature. Forgot the T. Okay, so PLIGHT. Okay, you could put that right up here with this. So PLIGHT is a great way to remember an ideal gas conditions, how you would make things more ideal. Now, again, the more ideal you get the gas, the more correct your calculations would be when you actually experiment with gases. All right, so that's the big deal on this. Okay, so again, the further you get away from ideal, the bigger the gas, the higher the GFM, the larger the gas. The most ideal, the more you get away from larger gases and you get into hydrogen and helium. So lightest gases would be that. All right, so that's the best way you could do this. That's your introduction on the really the definition of a gas. Okay, and then from here on in, we'll talk about what are the gas laws. So we speak about these gas laws. Now we're going to figure out what they are. Okay, if you need to go back over this or ask some questions, don't be afraid to come to support and let me know your concerns. Okay, have a great day. Bye.